Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, let's dive in. We're setting coordinates way out there today, folks. Past Jupiter, past Saturn, all the way out to the ice giant.
Uranus, deep space, yeah. And we're looking at one of its moons, Ariel. There's some really fascinating new research out published in Icarus.
Fascinating is almost an understatement. The main takeaway, the big headline here, is that this research suggests Ariel. Well, it used to have a massive ocean under its icy crust.
A really massive one. We're talking potentially over 100 miles deep. That's about 170 kilometers.
Okay, hold on. Let's put that in perspective for everyone listening. 170 kilometers deep. How does that stack up against, say, Earth's oceans?
Well, think about the Pacific Ocean. Its average depth is only about 4 kilometers, maybe 2.5 miles.
Right.
So this potential past ocean on Ariel, it could have been something like 40 times deeper on average than the Pacific.
40 times. On a moon that's, what, much smaller than Earth?
Yeah.
That's kind of mind-bending.
It absolutely is. We're picturing this relatively small, icy world way out in the cold, dark part of the solar system, and it might have had this colossal hidden layer of liquid water.
Yeah.
It really makes you rethink things.
Completely. Makes you rethink the potential for water and maybe even heat way out there. So, okay, the big question then is, how? How did scientists figure this out just by looking at the surface? What clues did they find?
Yeah, that's the core of the research, led by folks like Caleb Strom and Alex Padoff. They were basically doing geological detective work.
Forensics on a planetary scale.
Exactly. They looked at Ariel's surface geology, which is pretty dramatic. That's a huge cracks and ridges. And they tried to connect those features to what must have been going on inside the moon and how it must have been orbiting Uranus in the past.
So reverse engineering the forces involved.
That's the idea. What kind of stress would you need to break the moon's crust in exactly the way we see it broken?
All right, let's zoom in on Ariel itself then. The researchers called it pretty unique in terms of icy moons. What makes it stand out?
Well, first off, its location and brightness is the brightest moon of Uranus and the second one out from the planet. It's the fourth largest, but still pretty modest in size.
How modest are we talking?
Only about 720 miles across 1,159 kilometers. To give you a sense of that, it's roughly the driving distance from, say, Tucson, Arizona, up to Salt Lake City, Utah. That's the entire width of the moon.
Wow, okay, so not huge, but clearly something dramatic happened on its surface. You mentioned this geological paradox. What's that about?
It's this weird mix of really old and really young-looking terrain side by side.
Old and young, how can you tell?
The old parts are just covered in impact craters. Tells you that the surface hasn't really changed much in maybe billions of years. It's just been sitting there getting hit.
Okay, makes sense.
But right next to those ancient, battered areas, you find these stretches of remarkably smooth terrain. And that smoothness suggests something wiped the slate clean relatively recently, geologically speaking.
Like paving over the old roads.
Kind of, yeah. The prime suspect is cryovolcanism. Icy eruptions from inside the moon that flowed out, froze, and smoothed over the older crust.
So internal heat, slushy ice, or water erupting. That already hints at something interesting happening below.
It does. But even more compelling than the smooth plains were the giant cracks and faults, the sheer scale of the deformation.
Right, you mentioned those. What kind of features are we talking about?
Massive fractures, really long ridges, and these complex systems called grabens. A graben is basically where a big block of the crust is just dropped down between two parallel faults.
Like a valley formed by stretching and cracking.
Exactly. And the key thing here, according to the paper, is the scale. These features on Ariel are described as being at scales larger than almost anywhere else in the solar system.
Wait, larger than almost anywhere. That's a huge statement. Bigger than the cracks on Europa or the canyons on Mars.
That's the claim. We're talking features that might stretch for hundreds, maybe over 1,000 kilometers. And these seem to be part of a global pattern, suggesting the entire crust was under immense tension.
Okay, if the cracks are that big, the forces must have been equally enormous. You don't get solar system scale cracks without solar system scale stress. Precisely. That's the fossil record we were talking about. To crack and drop sections of crust that large, the stress had to be intense, widespread, and probably prolonged. It points to two things working together. serious internal heat, softening things up, and really powerful external forces. And those external forces would be tides from Uranus.
That's the prime candidate. Tidal forces, the gravitational push and pull from orbiting Uranus. This incredibly fractured landscape became the input data for their computer models.
So they had the crime scene, these giant fractures. How did they use the models to find the culprit, the engine driving it all?
Well, the first step was meticulously mapping the locations and orientations of all these major structures using the old Voyager 2 flyby images from back in the 80s.
Right, our only close-up look so far.
Yeah. Then they fed this map, this pattern of fractures, into a computer program. This program was designed to simulate how an icy moon's crust would respond to different kinds of stress, specifically tidal stresses.
Okay, let's break down tidal stress. We hear the term a lot with moons like Europa or Io. How does it work, basically?
It's all about gravity changing depending on distance. When a moon orbits a big planet like Uranus, the side of the moon closest to the planet gets pulled harder by gravity than the center of the moon does.
Okay.
And the center, in turn, gets pulled harder than the far side. So the overall effect is that the planet's gravity tries to stretch the moon out.
Stretching it, like along the line pointing towards Uranus.
Exactly. And as the moon moves in its orbit, maybe getting closer and farther away if the orbit isn't perfectly circular, the amount of stretching changes. The moon gets squeezed and stretched, squeezed and stretched.
Ah, like kneading dough, almost.
Yeah. Or imagine flexing a rubber ball. It constantly changes shape slightly. For a moon, it might bulge towards and away from the planet, relaxing back towards a sphere as it moves. That constant flexing is the tidal stress.
And that flexing generates heat, right? Friction.
That's the key. It's called tidal dissipation or tidal heating. All that bending and flexing creates friction inside the moon, converting the energy of its orbit into internal heat.
Like rubbing your hands together to warm them up, but on a planetary scale.
Precisely. You bend a paperclip back and forth, it gets warm, eventually breaks. A moon flexing under gravity. Same principle, just over millions or billions of years. And that internal heat is what could potentially melt ice deep inside, creating an ocean.
Got it. So the strength of this tidal heating, this flexing, depends on the orbit.
Crucially, yes. And the most important factor dictating the strength of the tides is the shape of the orbit, specifically its eccentricity.
Eccentricity. Okay, what does that mean exactly?
Eccentricity is just a measure of how much an orbit deviates from being a perfect circle. A perfect circle has an eccentricity of 0. The more elongated or oval shape the orbit is.
Like a squashed circle.
Yeah, the difference between its closest point to the planet and its farthest point, the higher the eccentricity value.
And why does that matter for tidal stress?
Because a higher eccentricity means a much bigger change in the gravitational pull the moon experiences during each orbit. It gets stretched a lot more when it's close and relaxes more when it's far. That bigger change in shape means much stronger flexing, more friction, and way more internal heat generated.
Okay, so the modeling team basically asked, how eccentric, how non-circular did Ariel's orbit need to be in the past to generate enough tidal stress to create those gigantic fractures we see today?
Exactly. They ran the models backwards, essentially. And the answer they came up with was that Ariel needed a past orbital eccentricity of about 0.04.
0.04. Is that a lot? How does that compare to its orbit now?
Here's where it gets really interesting. Ariel's current eccentricity is tiny, almost 0. That calculated past value of 0.04 about 40 times larger than its current value.
40 times. That's a massive difference. So its orbit used to be significantly more stretched out.
Significantly more effective at generating tides, yes. Even though an orbit with E or 0.04 would still look pretty circular to the naked eye, the effect on tidal forces isn't linear. It ramps up much faster.
Wait, why isn't it linear? Why does a 40x increase in eccentricity cause way more than a 40x increase in stress?
It comes down to the physics of how that energy turns into heat. The amount of tidal heating generated goes up much faster than the eccentricity itself. It's often related to the eccentricity squared, or even higher powers, depending on the specifics.
Okay, so small changes in orbital shape can have these huge outsized effects on the inside of the moon.
Massive effects. It means that this past orbit at 0.04 eccentricity would have been incredibly efficient at churning up Ariel's interior, generating a ton of heat. Enough heat, potentially, to melt a very deep layer of ice.
That really puts it in perspective, especially when you compare it to a moon like Europa, right? Jupiter's moon, Europa, is kind of the poster child for tidal stress cracking its surface. It is. Europa's surface is famously fractured by Jupiter's tides, But get this, the model suggests that for Ariel to get its specific massive fractures, its past orbit needed to be about 4 times more eccentric than Europa's current orbit. 4 times more eccentric than Europa. Wow.
Yeah. So if you think Europa looks beat up, Ariel's past must have involved forces that were, in a sense, 4 times more intense than what Europa experiences today. It really drives home why the researchers described Ariel's features as being on a scale larger than almost anywhere else. The forces involved were just monumental. Okay, so we've got the cause, this incredibly eccentric past orbit generating immense tidal stress, way more than even Europa feels now. And we've got the effect, these absolutely enormous fractures and grabens on the surface.
Ooh.
But why does that require an ocean? Why couldn't the moon just be solid ice all the way through and it just cracked under that incredible stress?
That's the linchpin of the argument. It comes down to how the ice shell breaks. The model showed something crucial about the style of fracturing.
Okay.
To get those specific features, these really long parallel grabens where huge sections of crust drop down uniformly over vast distances, you need the outer ice shell to be able to flex significantly and globally in response to the stress.
And a completely solid moon wouldn't do that. It would just shatter differently. Exactly. If Ariel was solid ice from surface to core, even if it got warm and a bit soft inside, it would still basically behave as a single rigid unit. When you subject a rigid body to those kinds of massive, oscillating tidal forces, it tends to crack in a more brittle, maybe localized way. You wouldn't necessarily expect these huge, consistent, globe-spanning fracture systems.
So what does adding a liquid layer, the ocean, change? How does that allow for these specific giant grabens?
The liquid water layer acts as a decoupling zone. Think of it like a layer of lubricant between the outer, brittle ice shell and the solid, rocky interior or core of the moon.
Decoupling, meaning the shell can move somewhat independently.
Precisely. Because the ice shell is essentially floating on this liquid layer, it's not rigidly locked to the core. This allows the entire shell to flex, stretch, and relax much more easily and uniformly as a whole unit in response to those tidal pulls.
I see. So the ocean allows the entire crust to participate in the flexing, leading to these large-scale, consistent cracks when it finally breaks.
That's the idea. Without that liquid layer providing the slip plane, the decoupling, you likely wouldn't get the specific type and scale of features like the massive parallel grabens that dominate Ariel's observed terrain. The liquid layer facilitates that particular style of crustal failure.
Okay, that makes a lot of sense. The ocean isn't just a consequence of the heat. Its presence is actually necessary to explain the way the surface broke.
Yes.
The researchers put it really well. In order to create those fractures, you have to have either a really thin ice shell on a really big ocean or a higher eccentricity and a smaller ocean. So there's a trade-off between how thick the ice is and how big the ocean is, or how strong the tides were.
Right. But the key point is, under the plausible conditions dictated by the past eccentricity, you need that liquid layer. The ocean is the non-negotiable part of the equation to explain the geology.
Which brings us back to that mind-boggling depth, 170 kilometers.
Yeah.
How did they land on that specific number?
That figure represents the kind of ocean depth that would be compatible with the strongest plausible tidal stresses, the ones generated by that calculated past eccentricity of 0.04.
So it's like the maximum possible ocean size given the forces involved?
Essentially, yes. Given that level of intense tidal heating over a long period, the model suggests a significant fraction of Ariel's original water ice mantle could have melted, potentially creating an ocean that deep overlying the rocky core.
It's still incredible that we can piece this together from fractures seen decades ago, but you mentioned a limitation, the timing. Do we know when all this was happening? When did Ariel have this super eccentric orbit in this deep ocean?
That's the big unknown right now, and definitely a focus for future work. Orbital mechanics in moon systems are really complex. Moons interact, orbits evolve. Tidal forces themselves tend to make orbits more circular over very long timescales.
So this highly eccentric phase was likely temporary, maybe billions of years ago.
Probably. It likely happened earlier in the solar system's history. But pinning down the exact timing is tough. What this study does is establish the conditions required. It sets the physical boundaries the eccentricity needed, the maximum ocean depth possible, that any future model trying to trace Ariel's history will have to match. It's a crucial baseline.
Okay, let's broaden the view now. This research wasn't done in isolation, right? It's part of a larger look at the Uranian system.
That's right. This is actually the second paper in a series from the same team. They previously published similar findings for another one of Uranus's inner moons, Miranda.
Miranda. That's the one that looks like it was smashed apart and badly put back together, right?
Yeah.
Really bizarre surface.
Yeah, Miranda's geology is famously chaotic.
Yeah.
And the team's earlier work suggested that its weird features could also be explained by past tidal heating, driven by a period of high orbital eccentricity, likely also requiring a subsurface ocean.
So the researchers are talking about potentially twin ocean worlds orbiting Uranus, Ariel and Miranda.
That's the tantalizing possibility they raise. It suggests that maybe the conditions for generating significant internal heat via tides weren't just a fluke for one moon, but perhaps a more common occurrence, or a phase that multiple inner moons went through in the Uranian system.
That really changes the picture of the Uranian system, doesn't it? We tend to think of it as just this cold, distant, relatively quiet place compared to Jupiter or Saturn.
Absolutely. For a long time, Uranus and its moons seemed kind of dormant, just because they're so far from the sun, and the initial flyby didn't reveal obvious ongoing activity like geysers. But if Ariel and Miranda both potentially hosted deep liquid water oceans in their past, driven by internal tidal heat, well, that paints a picture of a much more dynamic and geologically active system history than we assumed.
It really underscores how important tidal heating is as an energy source, potentially everywhere in the outer solar system, completely separate from sunlight.
Definitely. It's a game changer for thinking about potentially habitable environments far from a star.
But we're still working with pretty limited data here, aren't we? All of this is inferred from that single Voyager 2 flyby back in 1986.
That's the frustrating part, yes. Our only close-up images are decades old, and because of the flyby trajectory and the way Uranus was tilted at the time, Voyager 2 only got good views of the southern hemispheres of these moons.
So we've only seen half the picture, literally.
Exactly. As Tom Nordheim, one of the study's co-authors, emphasized, we just haven't seen the northern halves of Ariel or Miranda up close. It's kind of amazing we can deduce this much from half a moon viewed decades ago.
Does that limit how confident we can be in these ocean models?
It certainly introduces uncertainty, but that's also where the predictive power of this modeling work becomes so valuable.
Predictive power, how so?
Because the models aren't just explaining the features we have seen. They're based on the physics of how the entire moon should respond to those global tidal stresses. So the models actually make specific predictions about what kind of features, like the orientation and location of major fractures and ridges, we should find on the unseen northern hemispheres if this whole scenario is correct.
So it's like they've drawn a map for a future mission. If we're right, you should find giant cracks running this way up north.
Precisely. They've provided testable hypotheses. They've essentially laid out the geological treasure map for a future orbiter or probe going back to Uranus. It makes the scientific case for a return mission much stronger.
Yeah, you can see why they'd be pushing for it, absolutely. The evidence is compelling. Potentially 2 ancient ocean worlds with specific predictions waiting to be verified. It really boils down to what the researchers themselves say. Ultimately, we just need to go back to the Uranus system and see for ourselves. Okay, let's try and pull this all together. We journeyed out to Ariel, this fairly small moon of Uranus. We saw its surface is covered in these absolutely enormous fractures and grabens, some of the biggest geological scars seen anywhere.
Right, evidence of massive past stress.
The only way to generate that much stress, the models show, was through intense tidal forces from a past orbit that was way more eccentric, about 40 times more than today.
An orbit potentially 4 times more eccentric than even Europa's current one.
And crucially, the way the crust broke, forming those specific global features, required the ice shell to be floating, decoupled from the core.
Which means there had to be a liquid layer in between. A subsurface ocean.
An ocean that, under those extreme past conditions, could have been over 100 miles, 170 kilometers deep.
Just a staggering volume of water.
And this isn't just Ariel. Similar evidence points to its neighbor Miranda potentially being a twin ocean world. It completely recasts the Uranian system.
Yeah, it shifts our view from seeing it as just cold and dormant to a place that was likely once incredibly dynamic, wet, and warm inside, thanks to tidal energy.
What stands out most to you from all this?
For me, it's the sheer implication for water in the universe. If these relatively small moons, orbiting a distant ice giant, could generate enough internal heat to sustain oceans this massive, it just reinforces that the ingredients for potentially habitable environments, liquid water, and energy might be far more common out there than we used to think, even in the really cold, dark places. It definitely makes you wonder. And it leads to a final thought, building on that idea of past oceans. If Ariel and maybe Miranda really did have these deep oceans billions of years ago, how long could they have lasted? That's the billion-dollar question, isn't it? How long can liquid water persist inside an icy moon once the period of intense tidal heating ends? Does it freeze slowly over eons? Could pockets remain liquid even today?
Because the duration matters, right?
For chemistry, it matters immensely. The longer you have liquid water in contact with a rocky core, especially if there's heat driving hydrothermal activity like vents on Earth's seafloor, the more time you have for complex chemistry to occur. Time for interesting molecules to form, perhaps even precursors to life.
So understanding not just if the ocean existed, but for how long, is the next big step.
Exactly. This work opens the door to investigating the whole life cycle of these potential outer solar system oceans. How long did they exist? How did they evolve? It seems the universe might be teeming with these hidden water worlds, vast and ancient, just waiting for us to explore them further.